This is section 1-2. We are going to estimate the instantaneous rate of change of y at that value of x, specified by a graph, a table of y values, or an equation. We'll be utilizing different types of functions as shown in the screen. Let's take a look at a function first, and we're going to state whether y is increasing, decreasing, or neither, and if that rate of change is fast or slow. So let's take a look at A. Pick 2 points that are close together, draw a line, and you can see the slope of that is positive, so it's increasing. We say quickly if the incline is more than 45 degrees, and so that's why we say quickly. All right, x equal to b, find 2 points very close to each other, draw a line. You can see that's a negative slope, so it's decreasing, and it's less than 45 degrees, it's slowly. If it's hard to tell, I'll go with either answer. At x equal to c, pick 2 points that are close. You can see it's neither positive nor negative, so we say neither. Here's another graph that we're going to estimate the instantaneous rate of change at x at t equal to 5. And I blew up the figure over here at 5. Take a ruler and draw a line, a tangent line that intersects the curve only at that point. Find another point on the line that you can read. And then with those 2 points, find the rise and the run. Okay, so the rate of change, and in Algebra 1 you called it slope, but in calculus we call it rate of change, is negative 56 over 4, which is equal to negative 14 feet per second. And again, this is just an estimate. So as long as your answer's in the same ballpark, we're okay. The mathematical name is called derivative. And it's negative because at this time it is decreasing. All right, let's take a look at a function. This shows a graph, and using the function, we are going to estimate the instantaneous rate of change from 1 inch to 0.5 inches. So from 1 inch to 1.1 inch. All right, so what we're going to do is we're going to take P of 1.1, which is the final, minus P sub 1, which is the initial, and that's the change in the output over the change in the input. Now we're going to put this in our calculator. So on our calculator, I'm going to put it in y sub 1, and so on our calculator it's going to look more like this. Now I know at P sub 1 that they told us it was 24, so I can just write 24 here, all over 1.1 minus 1. All right, so let's go over to our calculator, and notice in y equals, I've already put the function. Disregard y sub 2, we're going to use that later. And I want to find the rate of change, so I'm going to start with my numerator, parentheses, and then I'm going to go to vars, and I'm going to go y vars. I'm going to choose y sub 1, and I'm evaluating at 1.1, and then I'm going to subtract 24, and then I'm going to finish my numerator parentheses, divided by, and then my denominator, and then I'm going to enter, and this is the answer that I'm going to get. So at about the approximation at 1, the rate of change at 1 will be approximately negative 11.951, and I'm going to write dot, 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 because I know there's more decimals. But I know the label for this is percent, because that's the probability divided by inches. The rate is negative because the probability decreases as the number of inches increase. All right, in our next example, we are going to actually get a point that's even closer. We're going to go from x equal to 1.01 to x equal to 1. And we're going to, again, do the same thing. We're going to do y sub 1 of 1.01 minus 1 all over 1.01 minus 1. We're also going to be finding other x values that are close to 1, like x equal to 0.97, x equal to 0.98, x equal to 0.99. X equal to 1 is not going to be very helpful because if you put 1 into here, 1 minus 1 does not exist. And x equal to 1.01, which I just showed you right here, and x equal to 1.02. So we're going to be taking a look at finding the rate of change between these two, between these two, between these two, and so on. And we're going to do it not by hand, but we're going to let the calculator help us. Now, how are we going to do that? Well, we're going to do that by creating an equation for rate. And so our rate equation will be equal to the function minus the y value of the point that we're targeting, which is p of 1, all divided by x minus 1. So p of x, remember, is that 40 times 0.6 x, and we know p sub 1 is 24, all over x minus 1. And we're going to put our different values in there, like 0.97 and 0.98, 0.99. Let's see what happens at 1, and then 1.01 and 1.02. Now these all will represent the estimate of the instantaneous rate of change when I use the x equal to 0.97 and the x equal to 1. All right, let's use our calculator to help us out. I'm going to go to y equals, and I want you to notice that I've already put this into y sub 2. I'm going to go to table set, and I'm going to start at 0.97, and my table interval will be 0.01. I'm going to go to second table, and I want you to see all these values here in y sub 2. These are the estimates of the rate of change. Now right here, I hope you're not surprised that there's an error here, and when x is equal to 1, we're going to have 0 in the denominator, and that's the error. So you can see that the value before that is negative 12.29, and the value after that is negative 12.23. So as it's getting closer and closer, we're getting closer and closer to the exact value. Now, how can we increase our accuracy? Well, we can take these two estimates, which is negative 12.29 and negative 12.23, and we can average them. And when we do that, we're going to get negative 12.259 ... And you can see that this number is a number that's between these two, and that's the best accuracy that we're going to have with this piece of data. All right, let's go on to the next problem. This problem is dealing with a table. So how can we estimate the instantaneous rate of change when we have a table of values? And we're going to start off with at point 3. All right, at point 3, we are going to find the, let's take a look at what the problem is saying. The problem is saying that a mass is bouncing up and down, hanging from the ceiling. So at 2/10 of a second, the mass is 0.399. At 0.3, it's 5.89. So in other words, the y values are getting longer and longer, so the mass is going down. And the mass goes down at about 0.5, that's its longest according to the table. 0.6, it is less distant, so that's on its way up. It's going to be going up until 1 second when it's the closest to the ceiling that's possible, and then it'll start going down and the distance is getting greater here. Okay, the difference between these two distances is 1.85. The difference between these two distances is 1.53. And let's go ahead and take a look at the rate. So this is the difference in the distance, 1.85, and we're going to divide by the interval, 0.1, and we're going to get the answer, 18.5. Do the same thing here, 1.53 is the distance in the interval 0.1, and so our rate of change is going to be 15.3. Now to increase the accuracy, let's go ahead and average like we did a few minutes ago. And when we take 18.5 plus 15.3 and divide it by 2, we are going to get 16.9. So 16.9, and that's going to be feet per second when we label the number. And that's what we can estimate. How fast is it going? Well, at t equal to 0.3, we can estimate it at 16.9 feet per second. All right, now what do we know whether the mass is going up or down? Now remember, this is a positive value. In other words, the distances are getting greater. And when the distances are getting greater, that means the mass is separating itself from the ceiling more and more. So we say that it's going down. All right, let's take a look at 0.6 and 1.0. And here is the operation on how we go about it. Same operation. Notice that this is negative, which means the distance between the ceiling and the mass is getting less and less. So this is definitely when the mass is going up. This is negative, but very close to 0. So this may be close to the spot where the mass turns from going up to going down. Okay, and I added the graph here so you can see the different, here's the graph of these points here, and you can see the mass is getting greater distance, less distance from the ceiling, and greater distance, which is what we were talking about. Okay, meaning of derivative. The derivative of a function, f of x at x equal to c, is the instantaneous rate of change of f of x with respect to x as x equal to c. We did this numerically by looking at the limit of the average rate over the interval, and we also looked at it graphically by finding the slope. Definition of a limit. This word limit we've been using rather loosely, and after we finish the last overview, we'll be getting more into depth about limits. This is your first preview of the verbal definition of a limit. And I'd like you to practice saying it so that when we finally get to the limit, the words are going to start making sense to you. This is the end of lesson 1-2.